This is my lab 2, a motion of a falling object. Alright, so the table of contents. So we have the introduction and conditions, equations and key physics concepts, experiment and data, explanation of the code, and analysis and summary. Alright, introduction and conditions. So the lab purpose was to show the concepts of gravity and drag by observing a falling object along its position, along with the analysis of computational models. And initial conditions for the initial velocity is 0, so there's no velocity, and the position is 0, 1, 0, meaning the top of the meter stick. And the ball is dropped with no additional force to make sure only gravity and drag are in the force in the system. The position, velocity, and time is recorded until the ball reaches or hits the position of 0, 0, 0, meaning at the very bottom. Alright, so equations and physics principles used. So we have the position velocity update formula from Newton's second law, which is here, where the position is plus the velocity average times the time is equal to the final position, and initial velocity plus the net force divided by mass times time is equal to the final velocity. And the force of drag, which is negative b times v squared times v hat, which is equal to force of drag. Alright. Now experiment the data. Here's the experiment. You see the ball going down. Boom. And looking at the data given, here we see the ball starts out like above 1 meter, so 1 meter, and then it comes down like this throughout time until it reaches 0. And here's the numbers. Alright. Now code and explanation. So since mass is equal to 1, we didn't have to include ball dot velocity. We didn't have to include the mass in the ball dot velocity equation, since any number divided by 1 is equal to the number. So if you look at right here where we calculated the ball's velocity, usually you would have to divide this by mass, but in this case, since mass is 1, I decided not add it to make it more efficient. Now looking at this, we can see that the ball velocity was given by getting that net force, which in this case was just gravity, if you can see right here, times the delta, which is the amount of change of time it had, which added the velocity, and then we used that velocity equation to get the position. Alright. Now also, and on the one with drag, everything's the same except for the fact that on Fnet, we have added the drag force, which is going to be ball dot velocity dot y squared by negative, because it's going to be the opposite direction of the velocity, and then we just add that to the net force, and then everything is the same. One important thing that I did was right here on the bottom where it says if ball position dot y is less than equal to 0, meaning that if the ball has reached 0, 0, 0, it stops the program to make sure that when it hits the ground, it stops recording. And looking at the data, the first data looks like this. The one with no drag added, you see it falls down like that. Second one, the one with drag, you can see that it falls down like this. Alright, so analysis and comparison. Now looking at the three graphs, we can see that the one with drag and the one without drag, you can see the great effect that drag has on the system and how it takes much longer. And also, I found it fascinating that how the one with drag and the one that's real, even though it's a little different, but at the end it reaches 0 at about the same time. Now this could mean many different things. One of them might be human error because I might have tracked it badly, or other factors such as wind. Alright, velocity versus time in terminal velocity. So the top one here is the one without drag, and the bottom one here is the one with drag. So terminal velocity is when net force is equal to 0, meaning that gravity and drag are in equilibrium. The bottom one, and which means that so net force is 0. Yeah, sorry. And the one that best demonstrates this is the bottom one right here, where you can see as the graph travels down, it reaches a horizontal asymptote, which would show when acceleration is equal to 0, which means force is equal to 0. Now what if the object was initially thrown downwards, meaning the initial velocity was not equal to 0, it would have no effect on the terminal velocity, as the initial force / velocity has no effect on when the gravity and drag force are equilibrium. Like, it doesn't have any effect on it. All you would is make it reach it faster, and you can see that here, where we lifted the 1 meter position limit that was in the code to better demonstrate it. And if you see both of the graphs, even though they reach terminal velocity at different times, they all equal negative 3.12. That was my lab. Thank you.